Welcome back, guys. So far this unit, we've done a lot of just, hey, here's an expression, simplify it. We haven't really applied what we've learned about exponents so far beyond scientific notation stuff. So this lesson kind of shows us why we would maybe want to learn about exponents, kind of how exponents apply to real life. So we're doing today what's called exponential growth and decay. The first thing we need to do is analyze an exponential function. So it's exponential, this thing right here, because it has an exponent, like it's b to the x power. And a function, if you remember from first semester, is basically just like a relationship between x and y, where every specific x value has a unique y value that goes with it. You just need to know like what the different parts of this represent. So we get all mathy and we like generalize a formula with a bunch of different variables. So the general form of an exponential function is y equals a times b to the x. When we write this though, and it applies to a situation, we replace a and b with numbers. So you can kind of see on 1, 2, and 3 here what an exponential function that we will work with actually looks like. X and y remain in every function. We replace everything else with a number. So basically, I want to think about what does A stand for, what does B stand for. That's totally necessary to know to be able to apply exponents in this way. So A is what comes first in your function, and that stands for the initial value of whatever it is you're talking about. So you might be talking about like a bank account balance or a population of people or insects. You see this sometimes in like biology. And actually the example at the very back, talking about a population of 100 insects triples in size every month. And we can use exponential functions to figure out like how many bugs there would be after 10 months, which is totally disgusting, but exponents can apply to that. So A is the initial value, like whatever you start with. That's what initial means, like right off the bat, what are we beginning with? B, on the other hand, stands for the rate. So it's going to be like a percent. If we're talking about like the value of a car or the value of a boat, something that you bought and maybe got a loan on. So like this first example here, example 2 actually, says that the population increased by 3% each year. So the rate is like the percent. And I'm going to put in parentheses here an important note that we'll need to know when we get into examples. Yes, it's a percent, but you have to write the percent as a decimal. Okay, and I'll show you what I mean by that when we get to example 2. The x stands for something as well, so I'm going to circle that. That's the exponent. The x stands for the time, so how many years we're trying to calculate, how many months, whatever the time is, that's the x. Okay, I want to make one more note about the rate, and this one, b value, it's got the most written for it. It's the most complicated to find. Usually the initial value and the time are really easy to pick out in the situation. It's the rate that gives us some trouble. So if you notice on these first examples here, they always put the b value in parentheses. So you'll see that a lot. They won't use the little multiplication symbol. They'll just put parentheses around it. So here's the notes I want to make. We're either going to be looking at a situation where it's growing or it's decaying. Okay, so there's a big difference. We don't want to mix this up. The b value tells us whether this is a growth function or a decay function. If the b value is bigger than 1, then it's going to be growth. If the b value is less than 1, it's decay. So it says like equals decay equals growth. So let's practice picking out which one's which in example 1 here. So they're saying identify the initial value, what's the a value, and then determine if it represents growth or decay. Okay, a value, easy to pick out, it's just the first number. So this one starts with 12. To say if it's growth or decay, you look at the b value, what's in parentheses. This time it's 1.05. If it's bigger than 1, it's growth. And I know that. Here's how I'm going to write it. I know that this is growth because the b value is greater than 1. Okay, example 2 here, the initial value, what I start with is 0.4. This one's also growth because the b value, what's in parentheses, is 2, which is obviously bigger than 1. And then example 3, so the a value, the initial value is 5,000 on this one. And let's see, the b value, what's in parentheses, that's 2/3, which is smaller than 1. So if it's less than 1, it's a decay function. And I'll write my explanation why b is less than 1. Okay, hopefully that's not too complicated for you. You're going to be asked to use a situation, write an exponential function to represent it, and then we're going to use the exponential function to tell us something about the future. So example 2, the situation is the population of a city is 5,000, and it increases, I'm going to circle that word, by 3% each year. I want to write an exponential function to represent the situation, and then I want to tell how many people live in this city after 5 years. Okay, this is like real world stuff that might actually be useful to figure out. Somebody somewhere is going to probably be looking at population models and want to figure this out. Now, the a value, pretty easy to pick out. It's just what you start with. So in this case, what did the population start as? Well, it started at 50,000, sorry. So that's my a value. That's what I started with. Now, the b value. So, okay, that's the rate. That's like the percent, what it's increasing or decreasing by. Now, I know that it's 3% on this example. I told you that you have to write the rate as a decimal for this to kind of work out correctly. You can't say 3. You need to put this as a decimal. So if you're not sure how to do that, let me show you. 3%, so the decimal is normally right there after the number. To turn something into a percent, you just move the decimal 2 places to the left. So that would be 0.03. Okay. Now, the word increased here tells me that I know that this should be an exponential growth decay or function. If it's growing, it's increasing, it's got to be a growth. Obviously, it's not decay. That would mean the population's declining, but it's going up. Okay, so I have to think about this here. Now, once you find the a and b values, you're good to go. You're ready to write the function. Those are the 2 things you have to pick out. So the a value, like I said, is usually given. It's really easy to find. It's going to be the b value that takes work. Now, we already identified this is increasing, it's growing. It should be a growth function. Growth rate is what I told you up here, bigger than 1. So there's a small problem with what I've done so far. I wrote that the b value was 0.03, but if I use 0.03 as my b value, this isn't right because this b value is less than 1, which would mean the population's declining. It's a decay. But I know it's increasing, so this cannot work as my b value. It's smaller than 1. Okay, this is incorrect because when it's smaller than 1, it's actually a decay function. And I definitely want a growth function. Okay, so we've got to think differently about how we find the b value on this example. Now, huge note to point out right here. This is really important. To find the b value, you take the percentage, okay, so this one was 3%, and we showed you that you write it 0.03 to put it as a decimal. To work out the b value, you take that percentage, and you're either going to add it or subtract it from 1. Okay, so this is the part that people make mistakes on. This is worth noting. Okay, so if it's growth, You want to take 1, and you want to add on whatever the percent is, and we'll generalize that as r. If it's a decay function, you want to take 1 and you want to subtract the percent at which it's decaying, whatever it is that you're talking about in the situation. Okay, so you're going to add on the percent or subtract the percent from 1 to find your b value. So that way this is accurate. Okay, so go back to the previous example about the population of this city. We knew that A was 50,000. That hasn't changed. The b value, okay, so instead of just taking the percent, writing it as a decimal and going from there, I know this is growth, and you're going to have to like identify on your own. Is it growth or decay? But hopefully the way they write it, it's pretty obvious. These two are big, important to note. The b value on this one, since it's growth, I need to do 1 plus the percent, 0.03. Okay, so that's going to give me 1.03. And this makes sense because like the 50,000 people are going to remain. That's why it's like a 1 on top of it. That's like the whole population that you started with. On top of that, you want to grow 3% more. So it's 1.03. So now that I've got an accurate b value, this is bigger than 1 now, 1.03. So this is going to be accurate. Now I can put a and b together to write my function. So when you write the function, write the general form like up top. It's going to be y equals 50,000, my a value. Put your b value next to it in parentheses. This time it's 1.03. That's going to be accurate. And then raise it to the x power. Okay, so there's my function. Now I can use the function to answer the second part. Tell how many people live in the city after 5 years. Well, the x is just the time. So if I want to know how many people live there after 5 years, I'm just going to plug in 5 for x right there. Okay, so now I'm going to take it to my calculator. Hopefully you got your calculator. And I'm going to do 50,000 parentheses 1.03, close the parentheses, raise that, so use the caret button, to the 5th power. So this is how many people would live in the city. Let's write an answer that makes sense. So it's 57963.7 or so. Yeah, you can't really have 0.7 of a person, so for the sake of this making sense, let's round it up. And I'll say about, that's what like squiggly equal sign means. We'll say about 57,964 people. All right, that's some decent growth there in 5 years. Almost 8,000 people, more people, moved to the city. All right, that was taking it pretty slow. These next two examples, last two, will go a little bit faster. So same deal. You want to write the function and then use it to make a prediction. This time the situation is a new car cost 20 grand and it depreciates. If you don't know what that means that the value of the car goes down. And when you buy a car, you guys, every day it depreciates in value. It's just getting older, you're using it more. So if it's depreciating, this should be decay. Value's going down. So the car depreciates in value by 16% each year. We want to write an exponential function to represent the situation and then figure out how much your car is worth after 7 years. You all are going to buy a car one day. This is legit, real life, something you might want to figure out. All right, you got to find A and B. A is easy. It's the value that it starts at. 20 grand. Okay, B value, be careful. The number one mistake people make is they'll just say, oh, 16%. Move the decimal 2 places to the left. Boom, 0.16. Do not do that, okay? Yes, that's less than 1, which would represent decay, but you cannot forget this note right here. You have to either do 1 plus the rate or 1 minus the rate to get your accurate rate in your function. So this one's decay, the value is going down, 1 minus r. So I need to do 1 minus 0.16. Okay, if I do 1 minus 0.16, that's 0.84. The reason you do that, you guys, so the car depreciates in value 16% each year. So that means 84% of the value remains intact. That's why we use 84%, 0.84, as our rate in our function. Okay, so be careful. That's the place that people mess up. I'm going to star that. Put it all together. So I'd say y equals, the A value is 20 grand, put your B value in parentheses, raise it to the x power. To find out how much your car is worth after 7 years, you plug in the time for x. So I would just stick 7 in where x is. Obviously, you need a calculator to work this stuff out, so hopefully you got one. And then I'd raise that to the 7th power. So my car is worth about, I'm going to round it out so it makes sense money-wise. Yikes. Only $5,901 and about 81 cents. I guess that's not too bad. 7 years, that's kind of a long time to have a car. So depreciates quite a bit after 7 years, from 20 grand to a little less than 6. Okay, here's definitely a question that would be worth asking. So what if they say after 15 years, so you own the car for 15 years, the buyer decides to sell the car for 3 grand. Is that a fair price? Well, if we use our model here that we wrote for our function, I don't know, let's figure out, like, if you ever heard like Blue Book, that's how much a car, they tell you like how much a car is worth in at a Blue Book price. So let's say I figured out how much my car actually was worth after 15 years. So I'm going to just arrow up to my function in my calculator, and let's plug in 15 for x, not 7. So the car is actually worth, after 15 years, from my model's prediction, $1,462.92. So let's see, if I sell it for 3 grand, no, that's definitely not fair, because the true value of the car is only what I wrote right here. So, I mean, yeah, you're making a decent profit there, but it's not a fair price. Good for you, bad for the buyer. Okay, last example. So here's where kind of like biology comes into play. And I don't know if you guys have seen this kind of example in biology. Tell me next time maybe. But a population of 100 insects, so there's 100 of them, it triples in size every month. Write an exponential function. Let's see, then find the number of insects after 10 months. So you got to find A, you got to find B. A is what you start with. There was 100 insects. Now, this example is kind of unique, and it's different than maybe the others. It's a little bit easier, if anything. You should see very clearly, okay, the insects are tripling every month. So obviously it's growing, the population of the insects, which is disgusting. If it says double or triple, you don't really have to think that hard about the growth factor or the rate. If it triples, your B value is just 3. If it were to say double, you can just do a B value of 2. So this one's a little bit easier and a little unique. So to write it all together, it would look like this, 100 times 3 to the x. And I'm talking about 10 months here, so that's what I plug in for x. Ew. Oh my gosh. So there is a ton of insects. That is like kind of unbelievable. But if it triples every month, after 10 months, there is almost 6 million insects. Totally sick.